We've already learned about dropout as a technique that we can use with neural networks to mitigate overfitting on the training dataset. How would we use dropout in TensorFlow when we are working with recurrent neural networks? We can use a built in TensorFlow library, the vocabulary processor, in order to generate unique IDs to represent every word in our input dataset. The vocabulary processor class in the tfcontrib learn library takes in the max sequence length of our reviews, basically tokenizes all the reviews into individual words and assigns unique IDs to them. Once unique IDs have been assigned to each word, it will then represent every review as a sequence of these unique IDs. Every review is now in numeric form. Set up a NumPy array of the labels as well. Remember, 1 represents a positive review and 0 represents a negative review. The size of our vocabulary is 21,097. That's how many words we have in our reviews dataset, unique words. Let's explore what we have here. Print out the actual review and also the numeric representation of this review. Remember, these are not the word embeddings, these are just unique identifiers that we've assigned to each word. These are two reviews picked at random from our dataset. Notice that the word like has a unique identifier of 60, and wherever the word like occurs in our review, we represent it using the ID 60. Both of these reviews are shorter than our maximum sequence length of 50, which is why they're padded with zeros. Longer reviews will be truncated to 50 words. And here are our labels. This should remind us that we haven't yet shuffled our data. Our data needs to be shuffled before we feed it to the RNN in the training process. I'm going to use some NumPy functions in order to create shuffled indices. I set up a random seed and get a random permutation from 0 to the length of our data. These are the shuffled indices. Shuffle the reviews in our dataset, shuffle the labels as well. So the reviews and the labels still match up. We'll now split our data set into training data, which we'll use to train our neural network, and test data, which we'll use to evaluate our neural network. We'll use 9,000 reviews for training, and the remaining around 1,600 reviews will be our test data set. Set up our training data in train underscore data and the corresponding labels, and the test data in test underscore data. We are now ready to set up our neural network. We start off with the placeholder for our training data. Notice that the placeholder tensor is of type int32. That's because all our reviews are now represented in the form of integers, represented in terms of unique IDs, which are integers. The shape of our placeholder is none, which represents the batch size. We have no idea the length of our batch at this point in time. And max sequence length. Max sequence length refers to the length of our review. We've padded and truncated reviews so that they all have the same length of 50. Next up is the Y placeholder for the labels. The labels are just integers, either 0 or 1. The tensor is of type int32 and we feed it in batches, which is why the shape is just none. Let's set up some parameters of our model. Our batch size is 25. Next, we specify the embedding size, which we set to 50. This is the dimensionality of an embedding which represents a single word. So every word is represented using an embedding or an encoding of dimension 50. Next, we specify the number of predicted labels or the num outputs. The maximum possible label is set to 2 because we have just two labels, negative sentiment represented by 0 and positive sentiment represented by 1. The embedding matrix holds the embeddings or encodings for all words in our vocabulary. This is a variable that is trained during the training process of our recurrent neural network. Randomly initialize this variable with numbers between -1 and 1. Notice the shape of the embedding matrix. There is an embedding for every word, which is why the first dimension is vocabulary size, and the size of each embedding is equal to our embedding size, which we've set to 50. Now, our reviews are going to be fed into the neural network in batches. There'll only be a subset of words from the entire vocabulary in each batch. We use the tf.nn.embedding lookup to look up those embeddings for words which are present in that batch. I've said this before, but it bears repeating that in order to understand how data flows through and is shaped by a neural network, it's useful to print out the shape at every step. Here, embeddings has a shape of none 50-50. The first dimension refers to the batch size, which we don't know yet at this point. The second dimension refers to our max sequence length, which is that every review is made up of 50 words, and the third dimension represents the embedding size or the vector size to represent one word, which is once again 50. The embedding matrix has an embedding for each word in our vocabulary. Our vocabulary is around 21,000, and each embedding is of dimension 50. We'll use a long short term memory or LSTM cell to build up this recurrent neural network. You can instantiate an LSTM cell using the tf.contrib.rnn.basic LSTM cell class. Make sure you pass in the embedding size because that will represent the number of neurons that we'll have in each layer of our recurrent neural network. Because this is a fairly deep neural network, it'll have 50 layers. Because 50 is our sequence length, we'll apply a dropout layer to avoid overfitting our model to the training dataset. Applying dropout to our LSTM cell is very easy. We simply call the tf.contrib.rnn.dropout wrapper, pass in the original LSTM cell, and pass in an output keep probability, which is 0.75 in this case. This keep probability indicates that a neuron in our recurrent neural network has a 75% probability that it will be active. There's a 25% chance for every neuron to be turned off at any point in the training process. A different set of neurons will be turned off at each epoch, and this is what forces the neural network to learn new patterns in the data. We use the same TensorFlow library as before in order to construct our RNN, the tf.nn.dynamic RNN. This looks at the shape of the inputs and basically unrolls the memory cell through time to whatever our sequence length is. The resultant tensors are the output states, the internal encoding or internal state of the RNN, that is the final internal state, and other specific state information. What we are really interested in is the encoding. Now, if you remember, RNNs require their input to be in a particular shape. tf.nn.dynamic RNN accepts inputs in the shape of batch size, num steps, and num inputs. And if you look at the shape of embeddings, which is what we pass into our dynamic RNN, that is exactly the shape. The shape matches perfectly. The resultant tensor has the output, the final state of your RNN, that is the internal state, and other state information. What we are really interested in is this final state or the encoding. And this is the final internal state of the RNN, which we'll now feed into a softmax prediction layer. Because this is a classification problem, the layer after the RNN will be the softmax prediction. And now things should be very familiar to you. We'll set up a dense layer, which is our logits layer. The activation is set to none because softmax activation will be applied as a part of the cross entropy function. Calculate the cross entropy, which takes in the logits layer, the dense layer, applies the softmax activation to it. It also takes in the labels and then calculate the loss using tf.reducemean. Find the predicted label using tf.argmax and see if the prediction is equal to the actual label by using tf.equal. Set up the operator that will calculate the accuracy of our prediction. Next comes the optimizer and the training step, pretty boilerplate. And now let's train our neural network for 20 epochs. Initialize the session that will execute our computation graph, iterate through every epoch, and for every epoch, iterate through the data in batches. We haven't set up the helper function to get our data in batches. No matter, we can simply set up the batch indexes right here. We calculate the start index and end index for every batch. Access the training data and the corresponding labels one batch at a time. Set up a feed dictionary and call session.run on our training step. Evaluate the loss and accuracy for training data as well as test data. We'll do the test data for every epoch and print out the results to screen. And that's it. Hit Shift Enter and begin the training process for your recurrent neural network. At the first epoch, our accuracy is only around 50%. It remains there for a long time. And at around epoch 6, it shoots up to 73%. And at the end of 20 epochs, the final accuracy that you get on your test data set is around 73%. It's pretty good given that we don't have that much data to work with, only about 9,000 instances in the training dataset. TensorFlow provides a built in library in the tf.contrib.rnn namespace called dropout wrapper. You simply pass in the memory cell that we are going to use within our recurrent neural network and specify a keep probability. The keep probability determines the probability that a neuron will be on during an epoch in the training phase of the neural network. A different set of neurons are turned off for every training epoch. This ensures that the neural network learns new patterns or new features in the data.